Hi, teacher Jerry here. Welcome to a short topic on the making of ammonia, right, which is mainly for the pure chemistry students. Right. This is one of the shortest topic for the pure chem. Okay, so basically we need to know that the ammonia, making ammonia, this Haber process is for the industrial. So you're talking about the large scale making of ammonia. Right. Mainly we use ammonia to make fertilizer, right, and make some cleaning reagents. So this is the Haber process, all right. In our lab, how do we make ammonia, right? We can recall what we learned, the base plus ammonium salts, right, will give you your ammonia gas and water. So this is for our lab. All right, in our lab, then this is the reaction that we produce ammonia gas. All right, okay, you can see that this arrow here, it should only be one mole, not two. Okay, and you can take note that this is a reversible process. Of course, there is a governing principle behind this reversible process, which you do not need to know in your syllabus, right? Just for just for your knowledge, it's actually known as a Lee-Chatterley's principle, right? So we know that this reaction will never go to 100% yield because every time you form ammonia, some of the ammonia will react back to form back like nitrogen and hydrogen. That's why it's reversible, means the reaction is going in both directions, right? Now, we will know that the volume ratio is also known as the mole ratio, but this is only for gas, okay? Because we know that one mole of any gas occupies 24 dm³ of space. So even you get a volume you divide all by 24, you come back to the same ratio. So technically, we know that where do we get nitrogen? Nitrogen is mainly from air, fractional distillation of the liquefied air. And then hydrogen is mainly from the electrolysis of water or cracking or your natural gas, which you're going to learn in the organic chem. Right, this is a set of conditions to allow us to get the maximum yield of ammonia at equilibrium. Again, when we say equilibrium, again, this is something for general knowledge, right? Means that the forward reaction equal to the backward reaction, right? Because when the rate of the forward reaction equal to the rate of backward reaction, it will appear that the reaction is not progressing, all right? So scientists have done experiment on different temperature, on different atmospheric pressure, and then this is what they decided that they get maximum yield. Right. So that means not only how much you produce, but also within a reasonable time and other conditions that we need to look at. When you get ammonia, condense the ammonia to liquid, and then you can collect back the ammonia. While the unreacted gases like nitrogen, hydrogen, they will channel it back to the reactant, and then it will react again to form ammonia, so that it will not be put to waste. Okay, as we understood that this reaction will be 100% complete. Experiment data has shown that the lower the temperature, the higher the yield. But why do we only fix at 400 or 450? Why not below? Okay, because when we lower temperature, the reaction also will also slow down. There's no point to get a lot of yield, but it may take a few years or take very long to produce. That's why we say, so these are the conditions, you see, not just the speed, not just the amount, but also the speed. And also we show that, higher pressure will give higher yield. Then how come why not we go beyond 200? All right, because uh, it will be expensive to create that kind of system, and it also not safe to operate in, dangerous to operate in. And then, of course, last but not least, ion catalysts. Do take note that catalysts are very reaction specific. That means ion catalysts will only speed up the Haber process. Okay, you cannot use any other catalyst. All right, so with this, I will end this chapter. All right, not much. It's just the conditions and why we choose these conditions. All right, see you in the next chapter.